If we buy an option and hedge with implied volatility, use the implied volatility to calculate the delta, the number that tells us how many shares to short per option. Well, what happens? Well, we don't know what the net is going to be at the end. That's what we're going to attempt to show, which seems bad. But the good part about hedging with implied volatility is we don't lose money on any given day or time step, let's say. And another advantage of implied volatility is we're not using the actual volatility in a calculation, so we don't have to be that certain on the actual value, because remember, we pretend like we have a way to calculate actual volatility, but it's kind of a fuzzy number. It's not a real, set, actual fixed volatility number for the stock. All right, let's start out with looking at we set up a portfolio where I buy the option. So I'm going to buy the option for V sub I, or V superscript I, because the option is priced using implied volatility. I short delta superscript I because I'm using the implied volatility to calculate delta. I short that much stock. So then this is what my portfolio is, and I have that much money invested in at the risk-free rate of return for one time step. So the change in this part is the change in my portfolio, and this is the change in my money. And the difference between these two will be the change in the net change in my position. Of course, the net always starts out at zero. Using a couple of facts then, I've got the function for the value of the call option using implied volatility, and I've expanded it out using Ito's lemma. Now, Ito's lemma would be, the derivative with respect to t, dt, the derivative with respect to s, ds, the second derivative with respect to stock, ds squared, but our ds then, when I square it, is going to end up with dt squared, too small, dt dx, too small, dx squared, that's a dt because quadratic variation, and that's why our ds squared is going to be sigma actual, because it's the movement of the stock, s squared dt. And that's where I get this Ito's lemma expansion of dv. I'm going to sub that in here. We've also got our Black-Scholes equation, which is true if I use the same volatility, and I'm using implied volatility throughout the whole Black-Scholes expression. So let's take this and replace this dv with this expression here from what we derived from Black-Scholes, and multiply this minus r dt through this bracket. So that would be minus v sub I dt, and then use my, replace this piece, r v superscript I, with an expression from our Black-Scholes. And let's clean up then. I'm going to have a minus r delta subscript or superscript is dt and a plus here. So this piece is going to cancel this piece. I have a sigma dt, a minus sigma dt, and a plus sigma dt. So these pieces are going to cancel. And I've got a delta is and a delta is. Those are going to cancel. Wow, so this really collapsed down quite a bit. And we can do some factoring, right? In fact, the only difference between these two expressions is the sigma actual squared and sigma I squared. So let's do some factoring here. I can take this to the outside of that bracket. And I can take the half outside too. Okay, so that's simplified great. There's my change in. Now, this is going to be, I'm going to prove this second bullet. We never lose any money on any given time step. So there's the change in my net, and we've made the assumption that the actual volatility is bigger than the implied volatility. So this bracket is positive, S is positive. If you look at the formula for gamma for a call or a put, they're both positive. So the change in this expression is always positive. So the change in my money is always positive. I don't lose money on any given day. That's a good thing. But I would like to now sum it all up and see what I make at the total and show that I don't know what I end up making at the total. So I'm going to integrate, I'm going to sum up all these pieces here. So for the total, I need to sum all these little changes from T naught when I first set up the hedge to expiry. Now we can take out some constants. This will be the total net. And I've got some, there's going to be a piece in here where I need to discount those little changes. But anyway, this isn't going to be the important part. The important part is here, that the stock changes every time as a function of time. That means gamma, gamma also changes. I lost my superscript I there, but that also changes. So the total here, summing up, is going to be different, or it's unpredictable, this total net, because it's a function of the way the stock actually moves around. So I don't know what the total, I don't know what the net, let's say, total is at the end. But I don't lose money every day, or I make money every day. Don't lose money on any day.